This week's lab is on the photoelectric effect, which is the effect that if you shine photons on a metal, electrons can be ejected from the metal. Every photon that hits the metal delivers an energy hf, Planck's constant times the photon frequency. Some of that energy goes into just removing the electron from the metal. The minimum energy it takes to do that is called the work function. The leftover energy goes into the kinetic energy of the electron. So the photoelectric effect is described by the equation Ke equals hf minus phi. So say you wanted to plot the kinetic energy of electrons ejected from the metal versus the frequency of the photons you were shining on it. If you measured the kinetic energies given known frequencies of light, you'd get a series of data points along a straight line. If you fit that data with the equation Ke equals hf minus phi, you'd see that the slope of your line is Planck's constant. The x-intercept, where the kinetic energy of the ejected electrons is 0, will be when hf equals phi. This frequency is called the critical frequency, and it is the minimum frequency that would cause electrons to be ejected from the metal. So in this lab, you'll plot the electron kinetic energy versus photon frequency, and you'll fit your data to a line to find both h and phi. You'll be given known wavelengths of light to use so that you can find the photon frequency, but you'll measure the kinetic energy. The light source in our experiment will be a mercury lamp with a diffraction grating mounted at the front of it. The diffraction grating separates the different colors of light from the lamp. The detector is attached to the source but can rotate to let in the different bands of light. The different wavelengths of each of the bands are given to you in the lab manual. When you're going to make a measurement using one of the bands, align the detector so that the band is passing through the detector aperture. Because it can sometimes get misaligned, you'll open the detector and look inside to make sure the light is hitting a second aperture inside the detector as well. The detector is essentially a capacitor that charges up due to the photocurrent. The voltage it charges to is the stopping potential. When electrons ejected from the metal have a kinetic energy equal to the stopping potential, the capacitor stops charging. You'll connect the output of the detector to a multimeter to record the stopping potential, but also to a Pasco box to record the capacitor's voltage as it charges. From the charging curves, you'll be able to deduce how charging current depends on the intensity of the light. To change the intensity of light, you can place a filter on the front of the detector that cuts down the light by either 0, 20, 40, 60, or 80%. When you make your measurements with either green or yellow colors of light, you'll have to use a green or yellow filter on the detector. This will help improve your measurements. To make each measurement, you'll start data acquisition in Data Studio and push and release the button on the side of the detector. This will briefly discharge the capacitor, so then you can measure it as it charges up again to the stopping potential.